Good morning, everyone. Hello. Oh, we have um almost good morning, almost as expected. Hi. We have fewer people, and that's okay. You get your normal routine going. So yeah, it's all good. And I see some more people here. Good morning, Nathan. Hi, everyone. Good morning, Robin, too. Um, yeah, so I actually just realized like 2 seconds ago, and you guys might, I forgot to text my mom good morning. it's it's a thing that I do. Good morning, Daniela. Good morning, Amir. So just to let her know I'm alive and all of that. So okay, I sent my text message. Now I really feel like I'm good to go. So guys, it's Tuesday. We're well, middle of the second week. I think we're ready to go with finishing chapter 4 today. We have a good chunk of chapter 4. I do think we have enough time to finish it. And then tomorrow will be dedicated to all chapter 5. Good morning, Mehmet. Hello, everyone. um, yeah, let me see. Let me see. Anything? I did some grading yesterday. I didn't finish everything, but I got pretty close to it. So I'll do the next big chunk today, and I that should include your exams. Um, if you if you take a look at your homework grades and you don't see a 10, which is the full score, um, just take a look at what you submitted. Mostly you want to see, did you do all the problems? Then you want to take a look at, did you submit on time? And then finally you want to look at, did you enough work show your work where anyone else can pick up your homework and get a good idea of what it is you were doing and what it is you were solving for. So take a look at that. The average score is almost a 9, so I think you guys are good for the most part. And if you turn things in late, that's okay. Just get it in. That's the point, to do it and practice it. Yeah. Any other questions? Just let me know, and uh, yeah, just let me know. We can figure it out. We can talk about it. Um, okay, let me think. Maybe we're ready to go. Chapter 4. We okay out there? Okay. Well, I hear no objections. I see okay. I see some okays, some thumbs up. Fantastic. Thank you. It's actually better, I'd like to get started on time and get as close to, wow, all the thumbs up, beautiful. I like to get started on time and finish to as close to on time as we can too. um, Although for this class lately I've been going over like a minute or two, but it's okay, as long as we finish off, it's okay. All right, I've started my screen, so now I'm going to share it with you guys. And so get ready to have all your windows rearranged. This happens as soon as we share screens. It happens on my end too. So now I'm just going to rearrange you guys so I can see you all. I don't know how other instructors that only use like their laptop or their tablet. I have, bless them, because Jesus, I do not know how they how they do it without multiple screens and being able to see everything. So I'm thankful that I had this already in my apartment. Yeah, yeah, it worked out. Okay, so you should see my full screen now. I see the chat and I see Luis's comment. Yes, having two screens is so nice. I'm so dependent on it now. I want like a third and a fourth screen. Like I want them everywhere. Um, yeah, I see your boxes. And so again, anything you need to add in during class, please do. Um, Okay, so we're about a third of the way through chapter 4. So chapter 4 has brought us into the motion of objects, and our overall goal in chapter 4 is to model different types of motion so that we always have a way to attack the problems. And so we're going to look at three major categories of problems. And the first that we saw yesterday was a projectile motion. And so what we did in projectile motion is we made two major assumptions. let's use blue today. We made these two major assumptions, and from these two assumptions, um, we were able to look at our kinematic equations and create a set of kinematic equations for any projectile motion problem. And let's remind ourselves that these kinematic equations are a combination of chapters 2 and 3, our vector math and our equations from chapter 2. So when you see a projectile motion problem, you can go straight to these equations and figure out which one to use based on what you have. That's one.
Hi.
Uh-huh.
So something I realized yesterday, I'm pretty sure like probably everybody else realized it before this, but like in calculus, we're given like a position function like x of t or something. And so what I realized that like that xf is like that is the beginning part of that.
Yes, that's right.
Like the final position, it just clicked that the final position was the position function, you know. I just kind of thought they were isolated for random variables. I didn't know I didn't think they were like isolated for like, you know, the final
Yeah,
answer.
it's good to make that connection. And you said something the other day to me, Randy, too, when you said eventually you get to a point where you just realize if you move this over to this side, it's just a change in position. And as physicists and engineers that have a math toolbox, our goal is always convenience. And so if we can set up a reference frame where y initial is equal to 0, right, then we've eliminated a variable and we're just solving for y final. And here's why we solve for y final. Usually we solve for things that we can see, right, and we can see how far something drops, we can see how far something lands, and that's a final position. If you have a stopwatch, something that we all can easily get, you can also solve for how long it takes for something to land, how long it takes for something to get to its highest point. So solving for position and solving for time is common. Um, Velocity we can solve for. We have the tools to solve for that. But many times it's given to us, you know, from a sensor data or something, right? But yeah, that's something really good to know, that having that, why is it that all of this is solved for final position, and it is a connection with math. And I see Daniela has a question. Same thing for time, right? It's technically a change in time in case we have a different starting point. Absolutely. The same thing here. This time, remember when we first started, we said change of time was the component in this equation. And this was the final time minus the initial time. And we want to get comfortable enough where we start to realize that we create the starting interval to be 0 at any point in the scenario, right? You could have, remember that one kinesiology problem where the person was running, but we didn't care about their takeoff. We cared about when they achieved the constant speed. And that's where we choose to start the time, the initial time. So yeah, for initial time, for time and for position, it's very much convenience. What is it that we're looking at? And really, what is it that we know? If we know some information, we want to isolate that time interval for only the things that we know. Everything else, if we don't know it, we can't do anything about it but complicate our lives. So, you know, we make that time interval and that position convenient for us. And mathematically, yeah, this function x of t and y of t is that final position if you set this to 0, which is what we want to do. Um, so those are great connections to make. And now we have this set of equations to use. Now, using this set of equations, there's a subset of problems that are also very common in projectile motion problems. And that's the next one. That's the second third of what we're going to look at today. So the next class of problems are very specific to objects that are thrown from some origin. Here's our origin, and here's our object. The object is thrown, right? We see it thrown in the air, and then and it lands in the same vertical position where it took off from. So if it takes off at y equals 0, through some time interval, it lands again on the ground and it is again at y equals 0. So this is an object that takes off from a horizontal plane and goes through its motion and lands again at that same plane. One example, my new favorite hobby is golf. So this is an example of a golf ball, right? You hit a golf ball, it goes its motion, and let's say you're on a flat green of some sort, it lands on the same exact plane. It doesn't go negative lower into the ground. You know, you avoid the sand pits, right? The lake and all that. And so this is an example. Any other examples out there of things that you guys have seen of an object that will act in this way? I will wait. Think about it. Mm. Oh
Football.
yeah, a bunch. Yeah, A bunch of you, and Kiam said football. Luis says soccer ball. Oh, Mehmet makes a good point. A bullet, if it leaves and moves straight and lands straight. I hadn't heard that one, and that's absolutely true. It can. Wow, that's totally true. Yeah, if the basketball gets thrown from a player's hand and lands in another player's hand at the same height, right? Nathan, your will to live. I don't know how we would physically measure that. but but if there's a way, as long
Birth
as
to
it doesn't
death.
go, yeah, as long as it doesn't go negative, right? um, yes, let's all send virtual hugs. Good morning, Nathan. Good morning. Yeah, so a lot of physical motion exists here of things that we can easily identify. And like any other physics problem, it's going to be in the wording of the problem, for you to identify, is this projectile motion? Is this projectile motion that lands on the same level as which it took off? We have to be able to identify that. And so in this class of problems, you can take the kinematic equations and the models that we just came up with and create a very specific set of equations that you can quickly solve for that position and that height that you're always looking for. So let us derive the equations, and I'm going to show you how to derive them. And again, I don't need you to know the derivations by heart. I need you to just recognize where they came from and follow along with the math. And then I will box in the equations that you need to know at the end. Okay, so here's our model, right? Returns to the same horizontal level. So let us take, actually the image is really big here. So let me make some notes here. So first look that we started at the origin. So we know the initial position y and the initial position of x is equal to 0. Then I want you to note that they have a velocity vector, an initial velocity vector. Once you see an initial velocity vector and you see the angle theta is also given to you, anytime you see this velocity vector, hopefully they give you a value, you want to think instantly, let me break this down into its components, right? So you want to say Vx initial is equal to, and you guys correct me if I get these wrong, I think this is cosine theta, and then Vy initial here will be um, uh, the initial sine theta, right?
Yeah.
The initial, thank you, the initial sine theta. Okay, so here's just some more information we have, and hopefully they give us this initial velocity, and then we can plug that in. And if they give us the angle, even better, right? We know those. Sometimes you don't know them, and you're left with an extra math equation. Okay, so the next thing we see with this particle that's thrown, at point A, it reaches this height. And so here, if we wanted to solve for this height, we can call this value of y h, right? At any point. I'll get to that in a second. And then gravity hits and it starts to fall, right? Because gravity hits at this point, we know that at the highest point that the particle reaches, the velocity at that position is equal to 0, right? Yeah, this is the point where gravity hits at its, not its largest value, but this is where the initial velocity kind of loses its power. At the highest point, gravity takes over and it starts to fall. And it falls then at some distance x, and here we call that r. R stands for range, What is the range of the particle thrown? And this h stands for the maximum height of the particle that's being thrown. So before we continue, I'm going to make two more scenarios here. The first one, let's say we look at the particle being thrown here and it reaches point A. So scenario one is up to here, up to here. So if we wanted to only look at this point, we could say this is T initial equals 0. And if we're only looking up to the point of A, we can call this T final, because this is our only scenario that we're looking at, only up to point A. And we can call that T at point A. T final is T at point A. This should really be drawn all the way out here, but you know, it didn't happen today. Let me see if I can do it quickly. Okay, we're good. There. Okay, because we're only looking at this time span. Now, if at this time span, Vy is equal to 0, what velocity is this? If this is velocity initial.
Velocity over 2?
No, we're looking at this Vy is equal to 0 here, and V initial is here, and this is our final time. So this would also be V final.
Final velocity.
We don't know over 2 yet, but you're in the right ballpark, Randy. We're gonna use that comment in just a second. So here, this Vy that's equal to 0 at this position, if we were only looking at this scenario from origin to A, then this would also be V final. V final in Y would also equal 0. So at this point, we have a lot of information there and we can solve for the height. Oh, one more, guys. If we're looking at this final position A, this height then, which would be normally Y equals H, this would also be our final position. So we could also call this H. Do you guys see this, the way we're labeling it?
Yeah.
Okay, so this is only if we're at the final here. Notice I can't say anything. I haven't said anything about X. We're not really there yet because X, we get more information at point B. Okay, let's leave that one. And now let's look at the time frame starting at the origin at the next scenario all the way over here. Now, if this is T equals 0, Randy, you tell me, if it takes, at this point, we're at T sub A, what are we at this point? What do you think?
2T.
Yeah, twice that T. So here, the final T is equal to, and I'm just going to put in an extra step so that we know what it is we're talking about. The final time is at point B, which is equal to 2 times T sub A. And this is 2 different scenarios. I probably should have done this in a different color. Right? This is 2 completely different scenarios. And again, this is what I think Daniela was saying earlier, that with the time, we can pick our intervals. Now, if we're moving all the way to position B, what is our final X here?
0. The same as X initial. Or no, wait, never mind.
That's Y, right? That's Y. So what Randy said was Y final was 0, but what about X final?
Oh.
It's
2R? Oh.
No, see how R goes? The R goes the whole direction, right? So then this would be R. So we could relabel things in terms of what are the variables in the drawing. Okay, so we've done a lot of work here. Let's pull it all and actually start deriving. We're going to start with the first scenario from the origin to point A. I'm going to click over to the next slide, and this is going to minimize. So our goal, I have a spammer calling me. Our goal then is to find, in total, our goal is to find the height and the range in terms of what is given to us in the problem. And what is shown to us in this problem is this initial velocity vector, the angle, and we also know that gravity exists, right? So gravity, here's gravity. it exists. It's fun to draw it out there too. Yeah, it is just a range, and R isn't, you know, the vector R, you could draw vector R as an, you could draw R as a vector with just an X component, but here it's just a magnitude. And again, the range here, you can also say it's the displacement, right? Displacement in X. So you could also say that. Okay, so we are going to start by trying to find the height and the range. Because of what we did on the first slide, where we separated the scenarios, this first scenario from time equals 0 to time equals a is exactly where the height is at its maximum value, right? So we're going to use, we're going to start with the height a, and we're going to analyze everything we just did at point A. We're going to analyze the peak of point A. So think about everything that we have here now. We have that X component of the velocity, we have the Y component of the velocity, we have these initial components, and we have Vy finals equal to 0. We also have Y finals equal to 0. So if you were to take a look at your kinematic equations, you can solve for a lot of them here. And this is the one we're going to use. Let me show you what this looks like. Before you look at the rest of the line, just kind of focus on this first part. So this is the equation. Vy final is equal to Vy initial. This is usually plus a y t. And remember that gravity here is equal to ay. So actually I should write ay is equal to negative g. There, that's a little better, just to keep it clear. Okay, so we use that first equation. And again, if you were to look at the last slide and you look at all the variables that we have, this equation would become almost obvious, like, oh, this is the one we want to use. Okay, so we have this equation, and now we plug in everything we know. We know the final velocity here. We established on the last slide that this would be equal to 0 because our time interval ends here. So Vy equals 0 is actually the final velocity. So that's 0. Vy initial is this component here, which is V sine theta, Vi sine theta. So this is Vy initial. Acceleration then, here, is equal to negative g. And the time is equal to the time it takes to get to peak of A. And so what you can do here then, because our goal is to find this final position, and any equation that involves final position needs the time. So we're going to take this equation and rearrange it to solve for time. And so now we have the time it takes to get to point A is that y component over gravity. So now, question? Oh, okay. Okay. So now we want to look again at our kinematic equations. Now we have time, we have initial velocity in y, we have acceleration. We need to solve for that final position of y. I don't know if I mistakenly said we have the final position in y, but we don't. We have the initial position. Let me just write it down what we have. Y initial is equal to 0. We have Vy initial. We know that's Vi sine theta. Vi sine theta, right? We now have T sub A. And we also know that the acceleration in y is equal to negative g. So with all of these, we go to our big kahuna equation, and we see that they have a y final. Y final.
Oh, Professor, a real quick question.
Yeah.
Negative g, is it either g? Isn't it just g, or because the g is negative, or?
Yeah, the g is negative, but let me see. How do I?
Like if you plus a negative g there, then it would be negative, like plus minus g.
So what if I wrote it like this? I mean, I don't know if this makes it any better for you guys, but we always want to remember that gravity is pointed downwards, right? And so in vector form, we can say we're adding it, right? In vector form, we say Vy final here is equal to V initial plus A vector T. In component form, then that's when we would write Vy final. You can ignore this Y here. Is equal to V initial. And the vector A, although the value is gravity 9.8, it's pointed down. So we need to have that negative there.
But like, it makes more sense to, since we know it's negative, it makes more sense to add it and then add the negative value.
Yeah.
Because I think it's like thinking about subtracting a negative value. So it's going to be like positive going the other way.
Yeah, I'm totally with you guys, and that's the way I would write it too. So if you feel more comfortable with writing it this way, we can do that.
Yeah, definitely.
Yeah, that's actually the way I solve my problems too, my physics problems. Plus AY 1/2. Uh-oh. I'm on one here. Oh hell. Oh hell. Okay, so is writing it this way what you guys, some of you prefer?
Yeah.
Yeah, I would, because I assume that, you know, it's ingrained that I know that gravity isn't a negative downward force, so
Yeah.
I start to get really confused if it's negative G.
I do. Sometimes I think of it as a second set of equations that is just going to confuse me. So I agree with you guys, and this is the way I prefer to write it. But so I'll write them out so that you can see where it came from. And here's what's really nice, that if you start with writing out your variables like this, and then you write the equation that you have, notice how we don't even have to think twice about where does the negative sign go. You just plug in everything you have. So y initial, for example, here and here, then becomes Vi sine theta, which you see here. Y final is the height according to the image, right? So Y final is the height. Now we have, oh gosh, sorry. Did I mix you guys up? No one said anything. Okay, so Y initial is 0. Y initial goes to 0, as you see here, right? Vy initial is Vi sine theta, so that goes here. We solved for T, and T is right here. So we're gonna plug this whole thing in for T, and you see that here, Vi sine theta over G. And now for 1/2 AY is negative G, so you plug in the negative G for AY, and now you have negative 1/2 G and T squared. We bring in the T and we square it. Okay, and from here now we're just going to start eliminating things, right? Let's see, what do we have? Vi sine theta and Vi sine theta, those become squared. So not an eraser, but that becomes squared. And you guys make sure you're doing this math with me. This becomes squared minus 1/2 G Vi sine squared. This is a G and this is a G squared. So one of these G's will cancel out. And then we're just left with 1 G. Is that right? Are we all okay there?
Yeah.
Yeah, so far so good.
Okay. So what you're left with when you do this math is basically 1 minus 1/2, and 1 minus 1/2 times this Vi sine theta I squared, Vi sine theta squared, right? Maybe I could do it on the side if you guys want to make sure I don't lose anyone out there. So this whole thing is squared over G. And then we subtract here. This is squared. One of these G's cancels out, one of these cancels out, so we're left with minus 1/2 of
So
the same.
these subsequent steps after like the first one are like substitution, right?
Yeah, it's all substitution. Yeah, the math stopped right here. I mean, the physics stopped right there. The rest is just math. But I just want to show you that this equation just becomes basically 1 minus 1/2, which is 1 minus 1/2 is 1/2, and that's the 1/2 that you see here. And so vi squared sine squared theta all get squared. And so that's what you have. Let me erase some things to make this a little cleaner. If this isn't at all clear to anyone, please, let me know. In the craziness of doing of doing all the math, I went back and forth a lot. So if you get lost anywhere, just please let me know. And so this is the equation finally. And what we see here now is a go-to way of solving for this height with only having the initial velocity and the initial angle and knowing the value of gravity. So here's a question for all of you. What do we plug into this G? Do we plug in 9.8 or do we plug in negative 9.8?
Negative 9.8.
Okay, I got two answers there.
9.8.
Okay.
9.8.
I hear more. Okay, the answer.
Just 9.8 because you already included the negative in minus half G.
So
Yes.
how can we fix it so it doesn't have that? Like
Okay.
where in the equation, like would it be?
All right, hold on. So the answer here is 9.8. The reason we're putting in 9.8 is because we've already accounted for this negative when we plugged it in here, right?
So if we change that sign to a plus, then it would be what we expect.
So if you kept it as plus AY and plus G, then at the end you'd have to put in a negative. And that seems, to me, that seems a little harder to keep track of. What I want to convince you of is that we've already accounted for the negative when we make this substitution at this step right here, right? We went from AY to negative G. So the negative is already accounted for there. So when you plug in your gravity value here, you're only going to plug in the number 9.8. Yes, yes. Okay, so as long as we're all on the same page there.
I get that, but it's just kind of. Sorry, go ahead.
Sorry. The equation that you boxed on the top with the plus sign, that's not the one you're using, right?
This is the original equation that we used, and after we plugged in all the variables, we ended up with this equation at the bottom here. But this equation that I boxed here is identical to the next equation here.
Okay, just that it has the plus half instead of the negative half?
Yes, but I don't want you to think of it as a plus half or a negative half. I want you to think of it as a plus AY or a negative G.
Okay.
So like if we waited to the very end to substitute in, we would have a negative there, but we didn't. We substituted in sooner.
Yeah, and if you wanted to leave AY in the entire time, you could. You could solve this entire thing and make the G's all AY and keep this as a positive. And then at the end, you could plug in AY equals G equals negative 9.8. So if you wanted to solve the equation with the original equation from the beginning and keep that the whole way through, you can absolutely do that. This negative would be different, of course. It'll be a positive of some sort, but your values will eventually work out. Yeah. Keon, you had a comment?
Oh, no, nothing. I was just saying, like, it's just a difference of remembering, of just keeping track of your negatives or deciding to say, it's just for me, gravity, to say negative gravity is like, things are floating away, so it's just easier to understand acceleration is usually gravity, and that's usually negative.
Yeah.
Negative.
Yeah. Yeah, it is a matter of that. And then I have another comment to me. Can we also say that height can't be negative? That's why G is not negative 9.8. So I don't want to say that that is true, because there are, believe it or not, in your future engineering courses, you're going to have your 3D space all flipped around. And there will be times when and I won't say that height is negative, height is just below the axis, depending on where you put your reference frame. The only time that G could be a positive 9.8 value and remain positive the entire time is if you take your vector that you drew here and you say that in the problem, right? You say that G is directed upwards. If you say that and you keep that in your problem, then you can keep it as a positive, and you know, your final solution will agree with this because this is in the problem. But you can't have a negative height.
Like if you jumped off a building, you would have a negative height because your initial height would be 0 and your final height would be like negative 432 feet.
Yeah, if you make the top of the building your origin, then the distance that you fall will be a negative distance. And what that means is that it's downwards, right? It doesn't necessarily mean that it's negative height. So we want to get really comfortable with, you know, making those physical distinctions using math, right? What does the negative mean? In our world, the negative will always really mean that it's opposing a direction, right? And in Physics 102, we're going to use attractive and repulsive forces. So that's where the negative word will change to a physical meaning. Okay, and Bafar says, anyway, positive or negative is the base on where we consider the original point in the direction. Yeah, the ultimate say all here is that wherever you put your reference and you make a nice big origin and you put your I hat and J hat on the paper somewhere, everything is referenced back to that direction, no matter how you write it. Okay, so this is a good example. This is an equation. If something leaves the origin at some height y and lands at the same y equals 0 some distance later, you could solve this problem with just this equation for the height.
Yeah, you could have negative time. If you like said 20 minutes ago and your reference point is now, 20 minutes ago is negative 20 minutes.
So Daniela's question in the chat says, what about time? Can it be negative? In physical meaning, no. In our mathematical calculations, yeah, we could set the origin to what Randy said 20 minutes ago, and we could say t equals 0. But does that like physically make sense? No, we would call it, you know, 20 minutes ago just means that it's in the direction past where we started our origin. But in physical real life space, no. Yeah, Luis, yeah, it's like distance. Yeah, we could set it based on a reference frame, but physically, like for real life, no. Mathematically, yeah, you could set up that equation. Okay, so now we have found the height. Let us now find what is the range. And because the range ends at point B, then we can analyze the peak of point B, again, given all of the values from this problem. So here we kind of start a little differently in that we are moving in the x direction, right? Yeah, we can't travel back in time yet. Yeah. Okay, so here we're moving in the x direction and we're solving for this displacement here. So this right away is a clue to, hey, our kinematic equations when we're in x all will eventually reduce down to that one equation in the x direction, to this one. Remember, when we're modeling an object being thrown, only this equation being thrown, only this equation is left amongst our kinematic equations. because we don't have any set acceleration in the x direction. So here we want to look at what we have, right? Do we have the x final position? Yes, that is going to be our point B. Do we have x initial? Yes, that's going to be our origin. Do we have the initial component of the velocity in the x direction? Well, yes, we know how to get this, right? And this is going to be VI cosine theta is equal to VX I, right? And do we have the time that it takes to get to point B? Well, if you remember, we came up with a relationship to the time that it takes to get to point A. So this is 2 times the time it takes to get to point A. And this is also our T final, or you can call it our delta T, right? All of these work. Okay, so let's plug everything in. So our final then, in terms of what we see in the illustration, our final position is the full length of R. So we use the range R, and R only means range for this problem. The initial X is 0 because we start at the origin here. The initial velocity then is, what is it? VI cosine theta. And the time, which is at point B, is twice the time it takes to point A. And so this goes to 0. Let me just make that clear. Okay, so now we can start solving and plugging things in. So VI cosine theta drops back down. The 2 comes back down here. And now we need to plug in TA. And I'll remind you of it by going back to the last slide. VI sine theta G. So VI sine theta G. And so now we have all this here. And what we can do is just rearrange the variables so that it's cleaner. We bring the 2 to the outside, the like variables together, VI squared, sine theta, cosine theta over G. So this is what we're left with. And up until this point, you have finished the physics. Now it's all math. And up until this point, perhaps you have a memory of how to reduce this equation. If you don't, that's okay. This is a derivation, and I will show you that. Maybe you remember 2 sine theta cosine theta as an identity of some sort.
Sine 2 theta?
That's right. I think that's right. It sounds right. Yeah, this is an identity of some sort. And again, this is a derivation, so you don't need to have this completely memorized. But if you kind of, thought it was familiar, yeah, that this is right. Yeah, Bifar says that was right too. So yeah, it's sine 2 theta. So let's plug that in. And now we have VI squared times sine 2 theta. And let me just extra remind you that this parentheses goes here. The 2 theta goes together, 2 times theta, and the whole thing times sine. And then divided by our value of G. And so this is now how you can find the range. You can find the range in terms of the initial velocity, in terms of theta, the angle, and in terms of the value of gravity. And this, if you stopped here, that's perfectly fine. But you could also maximize this value. The different values of sine and cosine will always be some decimal. So the highest value of sine and cosine will always be 1.
1.
So how do we maximize this sine of 2 theta? How do we get
sine? Set it equal to 1?
Yeah, let's set it equal to 1. Sine of 2 theta is equal to 1. What value gives us sine of theta equals 1?
45.
Sine of 2 theta will give, if it's 45, will give us 1, right? So if theta is 45 and we multiply it times 2, then we have 90. Sine of 90 is equal to 1. So at the maximum value here, the maximum value of sine in sine of 2 theta will be 45 degrees. And so our maximum range, we will get the maximum distance thrown of any object if you throw it at a 45-degree angle. If you go any bit higher than the 45-degree angle, your distance thrown is going to be shorter than it would be if you threw it exactly at a 45-degree angle. This is very useful in football, right? So I squared this because this is what you want to know. So now we have a way of solving the height and the range. And you could see this why it's so important to look at, let's say, the initial velocity and angles of an object being thrown. So here you can see now that because of the math and the way the angle works out, we know that there are complementary angles that will give us the same result for that R value, right? Yeah. And so if you threw a ball 5 different times, all with the speed of 50 meters per second, but you just varied the angle, some angles will produce the same range. So 15 degrees will produce the same range as 75 degrees. You'll get the same range. Clearly, we'll get a different height, right? We'll get different height. What else is going to vary in this motion between the 15 degree and the 75 degrees?
Flight time.
Yeah, the flight time, and I think I heard distance, which is if we follow the path of this motion, right? But the flight time is the big one, and Isla has it in the chat too. The time is going to vary completely, and only we will see one, by these angles, and by the initial velocity only in the y direction, because that is where that angle theta plays a role. When we solve for height, you see that angle theta in there. And so 15 degrees will give you the same distance as 75, but this one will take a lot longer. Luis says, is this something we should try to remember? The thing you should remember is this: the time of flight will depend solely on the velocity in the y direction. And that velocity in that y direction will give you longer times, shorter times, things like that. You can get the same value with 2 different angles. That's another thing you can remember. And this is a classic example of like Angry Birds, right? Of how you want to fling off, that's a bird, how you want to like throw, how you want to, actually, I think, yeah, major throwback. I have an old slide here. Yeah, you could hit that same piggy using different angles, right? You can go really low like this one is and hit it that way. Or you could do that same thing and just go really high and also hit that same piggy and just bury it. Scorched earth or worms too. Yeah. Yeah, this is real throwback, right? Let me try to find my slide. There's a reason I took that slide out. Okay, so that's all physics there that you just saw. Let's see if we could, make try this question. Can you go to the last window for a second, please? This window? So let's look at these launch angles here: 15, 30, 45, 60, and 75. Let's rank these. Which one do you think will take, no, the formula? Is it this one? I hope it's this one. Let's take the launch angles and see which one should take the shortest amount of time and which one should take the longest amount of time. 15 degrees, 30 degrees, 45. I think the other angle was 60 and the other angle was 75. Okay, I'm gonna click back now. And so, okay. Well, unfortunately, I clicked to the answer, but Nathan is correct. Yeah, the smaller angle will be less time. If you were to rank these launch angles for each of the 5 paths with respect to time, you'll see that the shortest amount of time is spent on the 15 degrees. And because we're following the path of this motion, it makes sense, right? Physically, that makes sense. And now mathematically, we can see that that makes sense too. 30 degrees will take long, 45 degrees will be right in the middle, 60 degrees will take longer than that, and 75 degrees, even though it's traveling, it's going to land at a shorter, a sooner a position before the 45-degree angle one. The 75 degrees will still take much longer in time. Yeah. Okay, so this is kind of our summary now for these, for all these equations, or our summary now, we can see it for how to solve these problems. Let me just put a quick timer Let's try a few problems. So let me summarize what we have in terms of equations and how we're going to solve all of this. Okay, so as you can see, there's a lot of variables going on in all of these problems, and it is a matter of organizing and finding all the information. So first two things you want to do is conceptualize and categorize. So conceptualize meaning kind of visualize what's happening, and then start to categorize what type of problem is this? What model am I going to use? So in conceptualizing, you want to think about what's going on physically in the problem and start to think of an image, right? You really want to get comfortable as a scientist with drawing a picture that doesn't have to be beautiful. It can just give you the information that you need, right? And with drawing that, you can start labeling different components. And then categorizing the problem is really figuring out which model are we going to use, right? We are looking at particles that are in free fall, which is a projectile motion. This free fall here tells us that AY will be that negative G value. I'm just going to put the negative in, but it's a G value. And that air resistance is neglected. So AX is equal to 0. And this then helps us dwindle down all the equations, right? AX equals 0 eliminates a lot of the kinematic equations. And then AY equals G will give us all of our equations with acceleration in the Y to be the gravity value, to use gravity value. And then finally, we have this special case of a projectile returning to the same level from which it landed. And when you see that, you know to use these equations. Okay, so you see a problem, figure out what's going on and try to draw an image if you can. Then think about what equations can you use, what model do you have? And finally, you start analyzing the problem. You're going to analyze the problem and then eventually, complete the problem. Analyzing means you need to start pulling out as much of the variables as you can out of the word problem. For example, if the initial velocity vector is given to you, v sub I, if this value is given to you, break it down into its components right away, right? Resolve it into its x and y components. And then start looking at what equations you can use. And so these are the two sets of equations that you can use. In the x direction, you can use this equation only. And then in the y direction, you can use the rest of the kinematic equations there. And if you want to, write them the way that you're comfortable with the acceleration, I recommend that. That's the way I also do it. AY sub t. You could do that too. And then finalizing, now you're just going to plug in all of your values, solve for what it is you're looking for, and just kind of make sure that everything makes sense, right? Does it match the picture that you does it mostly match the picture? Are the results realistic? Do the units make sense? If you're solving for acceleration, your units should equate to meters per second squared. Okay, I think I have like 2 or 3 problems we can solve, and then we'll take a break, and I think we'll be good to go. No, we'll take a break and come back, right? Okay, let's try this first problem. A long jumper leaves the ground at an angle of 20 degrees above the horizontal and at a speed of 11 meters per second. How far does he jump in the horizontal direction? So the first thing, again, always, you want to figure out what it is you have and kind of make a drawing of some sort, right? So here's our drawing, and it says an angle of 20 degrees above the horizontal. So that's our 20-degree angle, theta, right here. The initial is given to us, the speed, that is the magnitude of the initial, which is fine because we have the direction. And this is equal to, 11. That's an 11. 11.0 meters per second. And they want to know how far does it go in the horizontal direction. What are we solving for?
Arc.
What?
Arc.
R. Yeah, range. And I see Saja, Mehmet, and Owen also saying range. So right away, without me even saying anything about the problem, you're able to identify that this is one of those special case problems, right? Because he leaves and lands on the same position in the Y. So yes, we're solving for range, which is how far. So we don't even need to look at any kinematic equation. We just pull in the range equation, plug in our initial value for velocity and our theta, remembering that this is 2 times theta. And I say this because it's gonna happen on the exam. Someone's gonna mess up the 2 theta part. So just be very extra careful of doing that. Yeah. when I have included a problem like this, there's always someone that does it, and it's be careful. So the initial, no, Kiana, it's not going to be you. You guys be extra careful. So we bring down our sine, we include our theta value of 20, so sine of 40, what we're solving for, and the 9.8, we now know not to include the negative because the negative was in the derivation of the problem. And our answer is 7.94 meters. How nice is that? And how crazy far is that? That's so far that this person can jump. Okay. I hope you guys have that, and we're going to go to the next part. What is the maximum height reached? So in the last one, we solved for R. So I think now you know that we're solving for H here. Maximum.
For this one, can you just solve for velocity and find out and then set that equal to 0?
What?
Like, can you do the equation for velocity and when that's equal to 0?
And solve for height using a kinematic equation? Yeah.
Yeah.
You could do that, and I promise you, Randy, one way or another, it'll bring you back to this equation. So it's a really good point that Randy makes. You can, if you get lost and if you don't recognize what type of problem this is, and you'd say, you know what, it's just easier for me to use our kinematic equations, you can do that, but you need to make sure that you have all the components right in the equation, and it will reduce down to this equation. Totally fine to do that too.
So that equation there is like something that we would have for an exam or something?
It's for an exam, but it's for ultimately it's for this type of problem.
Okay, so it's not like necessarily memorizing that derivation. It's just you can use the equation.
Yes, what you want to memorize is that equation can be used for this type of problem.
Scenario. Okay. Yeah,
when something leaves and lands at the same y position, then you can use that problem. I don't know where I am. I think here. So now you can use the height. But for example, if we had, a building and someone throwing something off the building here and it lands over here, there is a clear height difference here, delta H. And so this here, this delta H, you cannot use this equation to solve for this H because they don't land at the same part, the same level. Yeah. Okay, so this is, we can call it a same level problem. So once you recognize that it's a same level problem, you can solve for this height right away. And just remember that the word height could be written in different ways, right? What is the maximum distance reached? How far up did the ball go? How tall? Thank you, Luis. Yes. How tall is the curve? What is the peak? Yes, that's another great example.
So I have a question.
Yeah.
Like, will it not, can't we, so say if you were to, at a 45-degree angle, shoot a cannonball up at, at a upward, straight. However, 2 feet after the point of launch in the horizontal direction, you have a cliff. Wouldn't the maximum height still be the same if you took it relative to the position that the cannonball was fired from? You would, at this point, clearly get a different maximum distance, but you would get the same height, right?
So you would get the same height, and this is a same level problem up until this position here.
Yeah.
Up until this position, you could totally use this equation. No matter, you can use this for same level no matter what. But the height,
Oh, okay.
the height that we're solving for here is the height of this peak.
Yeah.
Mhm.
But we couldn't solve for R. It would be different this time.
That's
Like
right.
the, okay.
Yeah, you could solve for R up to here, but if you wanted this R, you would have to use your kinematic equations as they are and not this equation. Yeah.
I remember once in a math test, we had to solve for like a golf ball being knocked off a cliff. And I was like, well, this is different, you know, like it freaked me out because I thought, but we were solving for the height. So it ended up not being different.
Yeah, maybe, oh, the height of this peak.
Yeah. The height, it
That's
didn't
true.
matter that the golf ball was being hit off the cliff or, you know, driven off the whatever they call it.
That's a really good point to make. So yeah, you could solve for it reaching its peak. And someone said to me, the word peak is a good substitution for this height. Yeah, it's up to us to recognize the problem. And if you don't recognize it right away, a drawing is how you want to start. And you know, the drawing doesn't have to be okay. It just has to show different positions in time. That's it. Okay, let's try another problem. A stone is thrown from the top of a building upward at an angle of 30 degrees to the horizontal with an initial speed of 20 meters as shown in the figure. The height from which the stone is thrown is 45 meters above the ground. How long does it take the stone to reach the ground? So again, here you want to start with your drawing, and once you have this drawing, you want to set up an origin that works for you. And because the ball is being thrown at the top of the building, and you get that angle of 30 degrees there, that's an indicator of where you want to start your origin. So notice that our origin here is at this position where the ball or the stone is being thrown. And so your axis is the same. X-axis, Y-axis, our angle theta. We have an initial velocity of 20 meters per second. And we know that the height from which the stone is thrown above the ground is 45 meters. So if this is y equals 0, you guys tell me, what is this?
Y equal negative 45 feet.
Yeah, negative 45 meters. And Owen Isla, and Owen says, hey, we're in SI units. So yes, yeah, negative 45 meters, right? And the negative 45 is what tells us that we're above our origin. That's pretty much it. From here, then, you want to pull out all the information that you know, right? Nathan says, I like to make the ground equal 0 and have y initial be 45. Y initial.
Like the initial height be 45 instead of 0.
Oh, y 0, like y initial equals 45.
Yeah.
And y final equal this.
0.
This will work. This will work. And as long as you're consistent in this, your answer will match your drawing. So that will work. I'm just trying to think of what else you might have to switch up because of that. It's not coming to me because I generally don't do it that way, but you can. You absolutely can. You just have to keep that consistent the whole way through. Yeah, it'll just, yes, oh, it makes a great point. Ultimately, we're in the kinematic equation, we're going to look at the difference in the height, and the difference is always that, just the difference. The value, that negative value, will carry through the equation and will just tell us about the direction of things. Okay, so let's pull out the information. We have an angle, theta is equal to 30. We have a speed, v initial is equal to 20, and we have 45 meters above the ground. And according to our origin here, this would then be our y final. And I say this is y final because when we land and this is not the actual trajectory of the particle or the stone. But when we land here, this is the y component, right? The y component is negative 45. And they're asking how long. So this should trigger to you, I'm looking for a time. Yes, we're looking for t delta t here. Okay, we'll take a break as soon as we finish this problem, and it should be in less than 10 minutes. So let's kind of go to the next page and pull over all the information that we have. Wow, I did that without even clicking anything. Yeah, I think it was my mouse. So this is everything that we have, right? We know the origin will give us the 0 values. Y final is negative 45. We know that gravity is going to affect the stone that's being thrown. So AY equals that negative G value. And then V initial is 20 meters per second. So going back to our problem solving strategies, ultimately we know we're solving for delta T. If we look at any equation that involves delta T, we're going to need more components. Mostly velocity in its component form. So we need to resolve the velocity into x and y components. We have it as a total speed, but we need it in x and y components. Okay, so Vx initial will be 17.3 meters per second, and Vy initial, Vi sine theta, will equal 10 meters per second. So again, notice just how helpful it is to know the full speed. We can break it down into its x and y components and eventually solve for something else. So before we move on to solving things, what is V final initial? V final in the x direction?
0.
Just before it hits the ground.
Oh, okay. I don't know.
It's the same because it doesn't change. 17.3.
Ah, thank you, Nathan. And I see a light bulb went off on Keon too. He was like, oh yeah. Yeah.
So the velocity doesn't change even though it has acceleration.
So Randy, make sure you note that we're in the x direction.
X direction.
It does.
Oh.
Yeah. So it does not have acceleration in the x direction because we're neglecting air resistance here.
So so like even if you're like, so say if you're throwing an object, like it doesn't ever have acceleration?
If the problem,
only when you're touching it?
If the problems will never, in our textbook and in our Physics 101 class, they should never have anything in the x direction accelerating it. It will have a velocity, but it will not have an acceleration that is going to change the rate of that velocity.
Okay.
Okay.
Thank you.
And I always have to remind myself, again, that acceleration is the rate at which that velocity changes. So we can have a speed, but we will not change that speed because nothing is acting on us in the x direction.
So it like leaves the arm with a certain velocity that doesn't increase or decrease. It only increased during which time it was in the person's hand.
That's right. That's exactly right.
Okay.
And so what I think it was Nathan who said it, that because we know Vx initial, you automatically know Vx final. That is not the case for Vy final because in y we have gravity. Okay, so let's just look at what we have now, and I hope this becomes obvious to you guys. We have y initial, we have y final, we have a sub y, and now we have Vyi. Looking at all of these and knowing that we're solving for time, our favorite equation comes into play here, right? We have y final, we have y initial, we now have Vy initial because we resolved that speed into its components. We have the value of gravity, and now we can solve for the value of t, which is, how long. So we plug everything in. Negative 45 meters, y initial is equal to 0, Vy initial is equal to 10. We're solving for t plus 1/2. Look at what they did here. They like to mess with us. This is what you guys prefer, and I do too. They brought the negative and just attached it back to the g so that it's plus 1/2 ay squared.
So they did it and then undid it?
Yes, and it frustrates me so much. They write it in the equation form, and then when they solve it in numerical form, they put it back in, you know, and it's like, what are you doing to the kids, you know?
The children, think of the children.
What are you doing to us? Like, it's not okay. But yes, they put the negative value in, but notice, you know, the positive comes back out if you put the negative in and attach it back to the G. Yeah. Oh, okay. So I don't know if this is a quadratic equation. I think it is.
And then that's where you get the positive and the negative answer or something. And then
Yeah,
that's why, but you have to neglect one of them.
that's right. So this is actually, and thank you, Nathan, for bringing that up. This is a quadratic equation, and you will get a positive and negative. And here you want to just think that physically we do not have a negative time for something that's thrown and takes place in present time, right? We start, we throw. So our
well,
time,
like it has a delta t, right? I guess, and then that can't be negative, right? Because a delta t can't be negative. It's only like it's like a displacement.
yes, I heard something different than when you said it, but now that you repeated it, yes, completely agree. The delta t, we could even add it in. Yeah, the delta t, that displacement of time is 4.22 seconds. That's pretty nice to solve this problem this way. Let's try the second part. What is the speed of the stone just before it strikes the ground? So notice it says speed, so we have to think of this as the total speed.
And so that's its max, right? It's going to be at its max speed just before it hits the ground?
Yes, that's a good way to think about it. So when we think of the max speed, in this case, you want to, you need all of its components. And let me just put in the finals because it'll, you know, it is that max speed just before it hits the ground. So, and I ask you guys again, which one of these do we have and which ones do we need to solve for? Which one do we have? This is yeah.
Have
Isla.
the X component.
Yes, Noah, thank you. Isla also in the chat. We have the X component. So remember when we solve, as soon as you solve for Vx initial, for this type of problem, we're neglecting air resistance, which is common. You're not going to see that in the word problem. You're just going to assume that that's the case. Then that will also equal Vx final. So now we need to solve for Vy final. But good thing is we have the initial, we have the acceleration, and now we have the time. So we can use one of our standard equations, right? And remember, this is the same as plus AYT. And we can plug in this initial that we got from the component of the velocity vector. We know acceleration, and we just solved for the time t. And now we can plug everything in. 10 meters per second.
So we're solving for the magnitude or the hypotenuse, right?
Yeah, that's right.
And that's VF. Is that where does the VYF, and you know, like where does that fit in? Is that a VYF or just a VF?
So this is a VYF and this is a VF. The problem is asking for the speed just before it strikes the ground, which we are going to denote as the final speed, right before it strikes the ground. The V final, the total vector, is made up of the X and Y components. And so we have the X component already. We need to solve for the Y component. And now that we have both, we can plug them in, right?
Oh, I see.
Yeah, this one was from the first page, and this one is the one we just, where did we get this one? Oh, we just solved for it right now. This one comes from here. And so then our final velocity just before we strike the ground is 35.8 meters per second. Woohoo! Oh man, we made it just in time. Okay, any questions right now before we take a break? Okay, I see no questions. Maybe you'll have some when we come back. It's about to be 11:15. Can we take a break till 11:30? How does everyone feel about that?
Sure.
Oh, I see lots of thumbs up. Yes, thank you. Okay, I see a bunch. Let us come back at 11:30. I have to use the bathroom so bad. Okay, see you guys soon. Hello. Just checking. Anyone out there?
Hi.
All right. Hello, hello, hello. Thank you guys. I see the hellos. I hear you. I see in the chat. Bonjour. Hello, Daniela. Hello, Robin and Owen and Saja. Mehmet, hello. Welcome back. Yeah, I hear you guys. So we're good that we're back there. Let me see. Okay, so let us keep going. We're on a good schedule right now. Let me just move around my Zoom menu bar. Yeah, we're on a good schedule, and we have, I think I mentioned, 3 models of problems. We finished the first third, we finished the second third. The first one being the projectile motion equations, the kinematic equations, the second being the same level problems. And now, here we go. We're gonna bring in everything we've learned in our past math classes, and we're gonna look at our third model of problems, which is circular motion. And different math is involved here because a circle can be a model of like a specific set of problems, and the math that is used here is particular to that symmetry of a circle, which is nice. Our forever goal in physics is to use symmetry to help us. Okay, so let's get some equations for circular motion problems. So first, we're going to look at problems that are in uniform circular motion. What this means is that this radius here is going to be kept the same, and so the circle is the same size as this car's, let's say, moving around. And so what we see in this image is a car that's moving in this, what are these called, like a roundabout thing?
Yep. That's
Yeah.
it.
Okay, thanks. Yeah, like it's moving in this roundabout, very popular in Europe and in some parts, not LA that much, but some parts. And here, just like we would in a circle, we would create our origin at the center, and we will draw our radius out from the center to the point of the object, which is at the edge of that circle, creating that circular path. So when we look at this, we know that the slope of any position over time graph or position over time equation, that slope will be the velocity. So you can see that velocity vector here. If we then look at the acceleration, we know that the acceleration will be the derivative of that velocity. So looking at this car, we could look at how the car moves in the circle over time and pull some information. So let's say this is the initial position of the car. So we can call this our initial here. And let's say at some time later, the car is now over here. And now the vector that describes this position is our final. As is usual, we can take this displacement here, and we can also find the velocity here. And now let's say this is the initial, so this would be the final. And from here, we can very much start doing some math based on just vectors and triangles that we know. So we haven't pulled in any circular information yet. Let's bring it over to the next slide and see what we can make. Okay, so here was our car in the initial position, and the vector that represents that position, and the initial velocity vector that represents that slope, that tangent of that position, right? At some time later now, we're at position B. And position B again is represented by this position vector, and this velocity vector, that's that slope or tangent to that. And if we wanted to, because of our vector math, we know we could take the displacement of that position with respect to the 2 vectors that are here. The 2 vectors that are here, we can also measure an angle theta between them. Okay, so we see this for position. We can do the exact same thing that we just did for the velocity vectors. So we have the velocity, the initial velocity vector with respect to this initial position vector, and then we have the final velocity vector here. If we take those 2 vectors and subtract them to find this change in velocity here, this is what it would look like. And this is if you preserve the angle and that angle direction. I hope that part is
So there. So the angle from the position initial to final is proportional to the angle between the velocity final and the velocity initial.
That's a great point, and I hope that you guys, that's absolutely correct, Randy, and I hope that you guys can visually see that. What we've done is taken these vectors here, the initial and velocity vector, and subtracted them to find that difference in velocity also, which is the same as or proportional to that difference in position. This might not seem as obvious graphically, but if I turn the triangles around for the velocity, now watch on the screen, if I turn this velocity vector around, perhaps now you can see the similarities between the two triangles and how Randy made that connection that this angle is also proportional to the angle between the velocity vectors. And so using this similarity that we see here, you want to recall anything you remember about similar triangles. And the thing you want to remember is what we just kind of drew out here, right? When two triangles are similar, they're considered to be similar if the angle between the two sides are the same for both triangles and if the ratio of the lengths of these sides are the same. So here you can see that this is uniform circular motion. So the length of this initial R is the same as the length of this initial, of the final position here. The length here is equivalent to the length here. The only thing that's different is the direction, right, in a circle. And so this tells us that the length of this initial velocity and the length of this final velocity are both proportional to the lengths of this initial position and final position. I hope that part kind of makes sense here. We're not saying that the lengths are equal, but we're saying that they're proportional. The ratios of them are proportional. So let us write out what a ratio would actually look like. So let me emphasize again that this initial position length is equal to this final position length. So I could write it in terms of their absolute values, right? Because the lengths are equal. And we can just call it R, right? And you can do the same for the velocity. Velocity initial magnitude is equal to the final velocity magnitude, and we can just call it velocity, right? We can do the same thing for just calling it velocity there. So now we can make a ratio of the lengths, and the ratio of the length is the ratio of this displacement to either one of these lengths, either initial or final, because initial and final are equivalent. So mathematically, this is what it looks like. The magnitude of the displacement of the velocity over the length of the velocity is equivalent to the ratio of the magnitude of the displacement position vector over just the length of any one of the position vectors. And let me remind you that this could be the initial or it could be the final because they're equivalent. This could be our initial or our final because they're equivalent. And you might ask yourself again, where the heck did this ratio come from? Why did we write this ratio? Again, this is from our similar triangle rules. And the actual definition of that is this, right? Two triangles are similar if the angle between any two sides is the same for both triangles and if the ratio of the lengths of these sides are the same. So we made a ratio of the lengths. So what we have here now, and this is just derivation. I should have said this, I'm so sorry. This is just derivation. Just follow along. So we have this equation here now, and we want to relate this back to our definition for acceleration, right? And so our definition for acceleration under uniform motion, right? Uniform motion would be the average acceleration because it's uniform everywhere. And the definition for average acceleration is that change in velocity over the change in time. So we can find a definition for this change in velocity from this equation that we made here. So we can solve this equation for delta V, bring over this velocity to this side, right? I'm going to cross it out and put it over here, and plug this entire thing into this delta V here. And that's what you see here. You see the V, the delta R times the delta T, and you see the V, the delta R, and the R. This delta T was from the delta T that was in the definition for acceleration.
So where's the purple V you drew?
Huh?
What is that? Like, I mean, what is it for? Why did you put it in there?
So this, I didn't just put it in there. This was the velocity that was down here. I crossed it out and solved this equation for this component here.
Oh, you cross multiplied?
Yes.
Oh, okay, I see.
So we're solving for this here. And so this velocity comes over to the side. And so now this whole component fits into where that velocity equation was. And again, you have the velocity, the delta R over the R here too. And this delta T just carries over. Now you guys tell me, does any of that, can we reduce this any further? Does anything look familiar perhaps? It might not be.
The delta R and the over the R is equal to the delta V over the V.
What?
The delta R over R
Is equal to what?
speed, or no,
So,
is
so
equal to.
I think you're right, Randy, but that's going to bring us into a cycle of equations, a cycle of substitutions. So you want to come up with something new here. And a new thing here, if anyone sees it, what is this delta R over T?
Speed.
Velocity.
Yeah, it's velocity. That's right. Thank you to both of you. So we could rewrite this as just V.
Doesn't that
T.
and isn't that constant? Like its velocity, isn't it? Like it doesn't change. It's not changing scale.
The magnitude might be constant if it, remains the same the whole way through, but the direction is always changing.
Yeah.
So notice that we're working with magnitudes here. And so in total, what we see is that the acceleration that we solve for in a circle and an object moving in uniform circular motion is V squared over R. So I'm going to bring that over to the next slide. And that's the equation you want to know. This acceleration describes only a particle that's moving in uniform circular motion. And when it's moving in uniform circular motion, we call that centripetal acceleration. The word centripetal means that it is center seeking, right? So it's revolving around a single point, and that point is described by the radius or the length of that circle. We always denote this with a sub c. The acceleration that you're used to seeing we can then call that a tangential acceleration. A t, a little t, or a big T. It doesn't really matter, but you can call that tangential versus this one, which is centripetal.
So its scale isn't changing, but it's like direction is, so it has a constant speed.
Yes. If this V is not if this V is uniform, then yes. Okay.
So if only the direction is changing, the speed can be the same, but the velocity cannot be.
Correct. That's exactly right. Yeah. Okay. So now with this definition, we can start to make more definitions that have to deal with circular components. So this is giving us an acceleration for around a circle, but notice that this is using a tangential component, and radius just defines that distance, but velocity is in terms of its tangential velocity. Can we then find an angular velocity, something like an angular speed? Yeah, we can. So we can look at the particle moving around the circle, right? It has a centripetal acceleration that is center seeking, and it has a tangential velocity. So let's try to get into circular components here. I should put on a timer before I lose track. Okay, so if we want to describe the motion of a particle with some constant speed in a circle of radius r in terms of its period, we can try to figure out the speed. And just remember, what is our original definitions of speed, right? We have some change in position over change in time. So you guys tell me, the change in position for a circle, if we say one full round around the circle is what?
2 pi?
Huh?
2 pi, or it's 2 pi r?
Yeah, so I hear it from Randy and I heard it from Isla too. The distance that we're now traveling around a circle would be 2 pi r. And this is considered to be one full trip around the circle or one cycle around the circle. One cycle is the definition of what we call a period. The period is a capital T, a large capital T. And so we can define this speed around the circle in circular components as 2 pi r over the period. So if you need the time, you would solve for just the period. And so the definition of the period is 2 pi r over the velocity. And this is again the tangential velocity. And just to be clear, notice that the letter V has not changed. So our definition for velocity has not changed yet. When we talk about angular speed, we're going to denote it differently, just like we did for acceleration, where we put that sub c.
I have a question.
Uh-huh.
So the delta x, is that like the radius?
No, this delta x.
That's the displacement, the circumference.
Yes.
Okay.
All I wanted you to remember when I wrote this is that it's a distance over time.
Okay, I see. So like it's usually if it's on the x-axis in one direction, it's got, you know, that x, but this case it's like the distance in a circle.
Yeah. So now we want to look at what is the angular speed. So what is that? So speed never changes, but angular does. What is that rate of rotation around the circle? So the rate of really, hold on, Randy, hold on.
Oh.
So the rate of rotation here will be that product of 2 pi, right, over that period that it takes to travel. The only thing that changes the length of that circle is the radius. So the rotation is really about 2 pi. So our definition for angular speed will start with just the circular components. So looking at just those circular or angular components, the angular speed defined as omega, this is little omega, will equal 2 pi over that period. We have a definition for the period right here. So we can take this whole component and plug it in there so that we can get the angular speed in terms of the tangential speed and actually calculate for it. So we plug in the definition of the period, right? 1 over the period, we flip over this guy and plug it in there. You see that the 2 pi cancels out and all that's left is V over R. So omega equals V over R, or the tangential speed is equal to the radius times the angular speed. The tangential speed V is equal to the radius times the angular speed here. So now we have the tangential speed in terms of the angular speed.
Can you describe like tangential speed? So that's like, is that like the
tangential speed? Tangential speed is the exact speed we've been working with. I'm just using the word tangential now. And the word tangential comes from it just being tangent to the line of the position.
So is that the magnitude of vector V?
Uh-huh, that's right.
Oh.
Yeah, it's nothing that has changed, but because we're going to use angular speed now, I'm just going to differentiate and call it tangential speed. But yeah, the magnitude of the vector V, that's exactly what it is. That's actually, we should write that down. Yeah, and it's good to make that connection that this is the same velocity we've been working with. Okay, so now that we have this definition of the velocity in terms of angular speed, we can also put this into our centripetal acceleration and now get the centripetal acceleration in terms of angular components. So A sub c then we saw was equal to V squared over R. And now we plug in R omega into V squared here. And so we have R omega squared over R, and one of the R's cancels out, and we're left with the centripetal acceleration is equal to R omega squared. And so now we have the centripetal acceleration in terms of its tangential components, and we have the centripetal acceleration in terms of its angular components. So whatever is given to us in the problem, we can use. I'm going to kind of summarize this on the next slide. So if you missed an equation, it's okay. It's going to be on the next slide. And here they are. All right, so centripetal acceleration is the speed squared over r. And this also equals r omega squared. Is it squared? Yes.
Yeah.
Okay, thank you. Yes, thank you, Ayla, too, also. We know the period is 2 pi r over v. If you ever forget where this comes from, again, this is just the distance around a circle, and this is the time it takes to go around one circle. And then this is just the speed. So this truly comes from our original definitions of speed. And now the angular speed is 2 pi over the period. We can also say that the tangential speed is r omega. Is it r omega?
Yeah.
Okay, thank you. R omega. So it's really nice that we can write everything in terms of its tangential components, linear components, and in terms of its circular components. This V is the same as writing this one. How do we write that? 2 pi r over period. And this period is the exact same thing as time, but the period denotes a full cycle. So if going around a full circle, or if you have a pendulum swinging, a full swing from beginning to the middle and back, or if you have a wave, right? You go from the crest through the middle, through the trough, back up, and back through the top of the crest. So you go a full cycle, basically. That's all the period means, but it denotes that time interval.
So I have a question just to sum up these equations. It would be acceleration, time, and velocity for rotation.
Yes, that's exactly right. And
Okay.
we have, let me write down what you just said. So we have acceleration and velocity and time. You could put position in there. I wouldn't write position, maybe distance would be better. Yeah. And for each one of these, we can write them in their linear components, and we can write them in their angular components.
Okay.
So this one is in the linear components, tangential. This one is angular. But let's be very clear that each one of these describes centripetal acceleration. Here you see this V this is angular. And this is linear. But again, this is in circular motion. This is the velocity of circular motion. Oh, V equals R omega squared. Is that right? Oh no, acceleration is equal to that.
So
V
centripetal
is
is
equal
just,
to r omega.
it's another way to say rotation, right?
Yeah, you can say circular, you can say rotation. What else can we say? Anything else?
Angular.
When you said
Angular?
centripetal, that's why I said,
That's why you said rotation? Because of the RPMs maybe? Yeah, all of these describe motion about a circle. How do you spell circle?
Revolutionary.
Yeah, revolution. That's a good way. That's a great word because when we talk about things in space, we usually talk about one revolution around, orbiting, things orbiting, revolution. These are all great words to describe that. And this is great.
Orbital.
Yeah, orbiting, orbital, revolution, revolve. Right?
so If we saw these words in like a problem, we could assume that maybe these equations have to do with solving that problem. I don't
Yeah.
know, just thinking about it, like which words are like analogous to other words for
Yeah.
physics problems.
Yeah, that's exactly right, Nate. And what you want to do is the minute you see this word, you'll draw it in that way with a circle, right? With something, when something orbits something, like when the Earth orbits the sun, the word orbit tells you that it's orbiting around like a circle. And so your drawing is going to relate to that word. And hopefully when you see this, you'll say, oh, I need my equations for circular motion. Yeah. So, uh-huh.
Does elliptical motion follow the same rules just with a different like radius and things, or no?
So elliptical motion, an ellipse is like parabola. Is that, what's an ellipse?
Like an oval?
Like an oval. Oh yes, thank you. Yeah, it will also do this. And you bring up a good point, and we're going to do this in week 5. But what you're going to see is that in nature, or at least in our solar system, everything does revolve in the shape of an ellipse, and it has elliptical orbits. But those ellipses are so close to a circle that we can model a lot of the math using circular motion.
Okay.
Yeah. So the level that an ellipse is is called the eccentricity, and the eccentricity is so low for some of these orbits that yeah, we're going to be able to model it as a circle, but we'll see that. We'll actually see that in week 5. Okay, let's try a problem. A particle moves in a circular path of radius r with speed v. It then increases its speed to 2v while traveling along the same circular path. The centripetal acceleration of the particle has changed by what factor? So you want to look at the centripetal acceleration equation that has to do with v's and r's, and then you want to do it twice. So scenario for the first one. Okay, I see some responses from Isla, Keon, and Nathan. That's 3 that all agree on D. So let's see how they came up with it. So this is the first scenario. The particle moves in a circular path of radius r. Here's radius r with speed v. Here's speed v. And what is the centripetal acceleration? That's this. The second scenario, centripetal acceleration, and now the speed is twice v. So 2v squared over r. And so when you square this 2, you are going to get 4v squared. And what you really want to do here is compare them, right? So how is v squared over r, how does that compare to 4v squared over r? And you can see here that that is then a factor of 4. Right? But this is how you want to mathematically support your problems like this. So when I say justify your answer, this is a way to write that. Okay. And if anyone ever, if you have to leave in the middle of class, that's okay. Be safe. Okay, so the answer here is in fact 4. Okay, let's try one more. Same scenario, but now they're asking, how does the period of the particle change? How does the period of the particle change? Remember that you're only given V's and R's, so you want to solve for that period. I don't remember the equation, but I know velocity is 2 pi r over the period. And so this way I can get
so the period is equal to 2 pi over v?
Yes, thank you. 2 pi r over v. Okay, and I see some answers in the chat already. Let me see at least 2 more if you agree or disagree. And so we can do the same thing. This is for the first scenario. And now for the second scenario, we can put in t. Okay, Noah agrees with Keon. 2 pi r. And just mathematically, you can prove this to yourself. And then this is 2v. All right, and Isla agrees too. Thank you. So the 2's cancel out, and now we have pi r over v. Did I do that right? Did I do that right? Did something come out right there? Should there have been like a...
Yeah. If
Yeah.
you put if you substitute in now 2v, right, don't you get 1/2?
Yeah. And so how does this one relate to this one? The second scenario is half that of the first one.
Yeah.
So the answer is a half. So the period here is inversely proportional to the speed of the particle. So you plug in the 2v. Thank you for that confirmation too. I appreciate it. Okay, so one last reminder of what the equations are, and we're gonna look at a word problem. So you have this set of equations, and you also have their angular versions and tangential versions. I'm just gonna add them in to make this complete. And what is it here? Okay, good stuff. Good screenshot. Okay, so we have some equations. Now let's try some problems here and see how far we can get on this. Okay, what is the centripetal acceleration of the Earth as it moves in its orbit around the sun? The radius of the orbit of the Earth around the sun is 1.496 times 10 to the 11th meters. So they're asking for centripetal acceleration, which is a sub c. They give us orbit of the Earth around the sun, and they tell us that radius. Okay, so if we draw this, let me see where I have some space to draw this. Maybe right here. If we draw this, right, we have the sun and then the Earth that's orbiting around. Okay, orbiting around, and this is a full circle. And they give us the radius from the Earth to the sun of the orbit. That's the radius, right? Okay, so they want the centripetal acceleration, and we know that the centripetal acceleration is, if we go back to our equations here, is v squared over r. They don't give us anything about angular speed, so that's probably not a way to go. But v squared over r, we also know we have r, so now we need to focus on v squared. And if you look at v, we know that we have another definition of v here, which involves the radius. Now we just need to know the period. Do we know the period of the Earth orbiting the sun? I see a lot of head shaking.
Yes.
Yes.
865.
Yes, thank you. Thank you, Nathan. Thank you,
Or
Randy.
525,600 minutes.
Or in seconds, we can calculate that, right? So here's our equation. Centripetal acceleration is v squared over r. We plug in our equation for v, 2 pi r over t. And so this is your equation. Notice we haven't plugged anything in yet. Now you can start to plug in and calculate. So 4 pi squared times the radius that's given to us. The period we know is 1 year, or 365 days, and you can include that conversion in there. Notice that the whole thing is squared. So mathematically, you need to square the entire thing for it to be equivalent. This is a place where I see a lot of errors sometimes. So make sure that they're actually equivalent. In my materials of engineering class, I see this a lot. So in those higher classes, you're gonna have to make a lot of these conversions. So just make sure that you square that too. Or if you,
we're squaring that because that's the substitution. That's what's underneath that thing.
Yeah, we're squaring it because the period is squared, and so the conversion has to be equivalent to that. For example, I'll just show you. If we were to keep the 1 year, the value here would be 1 year squared. So for you to convert this year squared, you need to have a year squared here. And this works out because once the year squared cancels the year squared, we're left with the exact unit for acceleration, which is the second squared. So this squared will square the number and will square the unit. And so now we have
So
this.
that conversion factor, we squared then. It wasn't innately that way.
That's correct. We squared the conversion factor to solve for this. Yeah. Okay, let's try one more problem. What is then the angular speed of the Earth in its orbit? How dare they? they want to know what is the angular speed. And so if we go back again to our equations, right? We look and we say, oh, our angular speed has there's several ways to solve this, but the go-to equation is this one right here, 2 pi over that period. And, that's the angular speed definition, right? So we go back, 2 pi over the period, 2 pi over the 1 year. And now the conversion isn't squared because it's not in the equation. And we get 1.99 times 10 to the negative 7 per seconds. So this is the same as saying 1 over second. And what this is really telling us is that this is a rotational speed. So if you really want to write the unit or feel like, hey, there's a spatial unit there, these are radians because we're moving in the circle, right? So you could say radians per second, or you could just write per seconds. You want to be careful about when you use radians. It's right to use radians, but for example, you just want to be careful with what the units are that are given to you. So angular speed can be given in radians.
So we're saying that this is, so like 1.99 times 10 to the 7th, it's not seconds, it's blank per second.
It's per second, which means that in angular, and its frequency, yes, or hertz, that's right. Those are the frequency is usually the unit of 1 over second, and the 1 over second is equivalent to the unit of the hertz. That's totally right, guys. And think about what you're physically saying. You are moving at an angular speed of 1.99 times 10 to the negative 7 per second. Angular is already telling us we're moving along a circle. And so you're moving 1 radian, or that value of radians per second. So it's not necessary to say the radian because we know we're in angular motion. I hope that part makes sense to you guys.
So what if we were to do degrees, like if we were to say 360 degrees in 1 year and then have degree per second?
So what is your conversion factor there, Randy? What is 2 pi radians equal to in degrees?
360.
Yeah. And so this would be your conversion factor, or you can say pi radians are equal to 180 degrees. And if I wanted to ask for a revolution, how many revolutions is 360 degrees?
1.
That's right. So let's say you calculate the motion is something like 8 pi, and 8 pi is something like 4. I don't know if 8 pi actually is 4 times 360. I think it is. I'm just saying 4 times around a circle, right? The number in radians might not make sense, or the degrees, something like 635 degrees might not make sense. So they might ask you to convert it to a revolution, and you will need to convert using these conversions, right? This is equal to half a revolution. And you'll see that sometimes it's much more practical to say this half a revolution instead of the degrees, or instead of saying pi radians. But yeah, if your answer was given to you in radians and they ask you how many revolutions is that, you would be able to make that conversion, yes.
So like to use degrees is okay if that's how we do it, you know?
No, you use degrees if they ask for degrees. If the
otherwise use radians no matter what?
Yes.
Okay.
Yeah, it shouldn't even come up. It should only come up if the problem says how many revolutions, or if the problem asks how many degrees. Then absolutely change it to degrees. Is this
Whenever
you wanted? Yeah. Okay. Go ahead. Okay.
whenever like I do my equation, I always the math teacher tells us not to like put radians because it's understood because there's a pi. Like
That's
I
right.
always put RAD next to it so that when I get to the end, I'm not confused by my unit.
Yeah, and that's okay. And I agree. We usually don't say radians because it's redundant when we know we're working in circular motion. But if, again, if that helps you remember, that's okay. It's okay to write it, but it's not necessary. Yeah.
Like I would maybe think at the end if I had a 1/seconds that I was like I had my units messed up or something.
Not if you know that the angular speed unit is 1/second. Or
Yeah.
when you get to physics 103 and we're working with waves, it's very common to solve for a frequency. And the word frequency does mean how many revolutions in this second, right? So when you use the unit of frequency, it's stated, but perhaps having this one here can certainly throw us off. So you want to get comfortable with it, but by physics 103, you'll be using 1/second or hertz pretty often. Yeah. Okay, so we have enough time, so I'm gonna finish off this slide set. Don't hate me. I'll describe the lab after. Let's just try it. Let's try. Okay, so what I've described so far is the centripetal acceleration, and I think earlier we were saying, wait a minute, what does the tangential acceleration look like? And it's just that it's tangent to that point of motion where we're analyzing, right? So at any instant, the vector, the total acceleration vector, can be resolved into its two components, just like an x and y component. And in fact, when we draw it out, we see that each one does resemble like an x component and a y component. So if we look at this path here, and at any point of the path, somewhere on the arcs, you can describe that arc as a circle. That particle, let's say at point A, has a tangential acceleration that it's tangent to that point, the slope of the velocity there. And it also has a radial acceleration, which is the same as the centripetal acceleration. So it has a centripetal acceleration and a tangential acceleration. The two together will give you the full picture of the total acceleration. So all of the rules we've used from here, from the past two chapters of vectors, we can use them here too. So the total acceleration would be the sum of the squares and the square root, right? So in vector notation, this is what it's written as. The total acceleration is the sum of the radial vector plus the tangential vector. This is the same as saying the velocity vector is the x velocity component plus the y velocity component. It's the exact same thing, or ax, ay for acceleration. So when we solve for these, the tangential is still the derivative of the velocity, or any other way you want to write the velocity. That's still, nothing has changed. And the centripetal acceleration is the same as the radial acceleration. The vectors are the same. They are measured from the center of the origin, the center of the circle outwards. And you're going to see now a negative sign. This negative sign that's here only implies how we measure the direction. Now notice that AR is the same direction as centripetal acceleration, A sub c, because it's center seeking. There is a fourth unit vector that we haven't gone over because we haven't seen it yet. We have the unit vectors I, j, k that represent x, y, z, and we have what we call a radial unit vector. A radial unit vector, I think that's how you spell it, radial unit vector r hat. Oh, of course I wrote an arrow. Say, write what you speak. R hat. And so this tells us what is the direction from the radius to the point on the circumference. So for example, we measure in our standard conventional way, the radius outwards, right? So the radial vector will always be pointed outward to the circumference. So let's say in this example, Do you guys see this big circle? There's this big circle here. The radius is somewhere, this origin is somewhere right here. So the radial vector is pointed outward. Notice that this radial vector is opposite to the direction of the radial acceleration. And that opposite in direction is where this negative comes from, because it is opposite to the radial direction. Radially outwards is opposite to center seeking. I hope that part makes sense.
Is that why it doesn't like go closer to the center or farther from the center because they're equal?
Yeah, yeah. Radial and centripetal will always be equal, but in our conventional way of directions in circle, we measure radially outward. And so the radial unit vector will always be out from the origin, which will give us that negative. But notice that the centripetal acceleration is the exact same value as v squared over r. It's the same thing, just with the negative, and this negative comes from that radial unit vector that is opposite direction. Okay, so now you have the magnitude here and the magnitude here, and we know how to solve this, right? Then the total acceleration vector, which is this guy here, the magnitude of that total acceleration vector is the sum of the square root of the sum of the squares, right? AR squared plus AT squared is the square root. So now we have a full picture of how to solve for total acceleration. If you wanted to write, you could just write radial. That's probably the best way to go, because you might forget the negative we see there. Okay, I hope this part is okay. Let's try a problem, right? A car leaves a stop sign and exhibits a constant acceleration of 0.3 meters per second squared parallel to the roadway. The car passes over a rise in the roadway such that the top of the rise is shaped like an arc of a circle of radius 500 meters. At the moment the car is at the top of the rise, its velocity vector is horizontal and has a magnitude of 6 meters per second. What are the magnitude and direction of the total acceleration vector for the car at this instant? So again, the first thing we want to do is have some sort of image drawn here and pull in all the information. It tells us that the car is exhibiting a constant acceleration of 0.3 meters per second. And notice that it tells us that it's parallel to the roadway. So this is the arc that the car is on, that rise, and it has a radius. And if it's parallel to the roadway, that means it's tangential. And so this value comes from the word problem. A sub t is equal to 0.3 meters per second squared. And here's the vector drawn out.
What's the sub t?
Tangential.
Tangential. Oh, okay.
Yeah, and tangential is the same linear components. And
So it's like perpendicular to the outside.
It's perpendicular to the radius here.
Okay.
Yeah, because we're measuring the radius here. Okay, yeah, it is perpendicular. Okay, then it says the car passes over this rise with a circle of 500 meters radius. So this is r equals 500 meters. And then it has a velocity vector in the horizontal and has a magnitude of 6 meters per second. So here's the velocity, 6 meters per second, and here's the vector that draws that out. What is the magnitude and direction of the total acceleration vector? So we want total acceleration vector, and we want the magnitude of this. And I think we know that this is eventually going to be the square root, right, of the tangential plus the radial.
Radial?
Yeah, yeah. And then we want that angle theta, right? And based on the drawing, we can see which is the y and the x, or the vertical and horizontal, right?
Is the A tangential and A radial, are they squared underneath the square root?
They are. Yeah. Okay, so we know what we need to solve for. We need to solve for this radial component. Luckily, they give us this value here. And so let's move over to the other side and see everything that's given to us. I hope we remember then, right, that this we have the velocity and the radius here. So this radial component is the same as the negative of the centripetal. So AR is equal to the negative of the centripetal, which is equal to negative v squared over r. And that's what you see here. They give us the velocity vector and they give us the radius of the circle. And so now we have that radial component, and so we can now solve for the total acceleration. We plug in that radial acceleration and the tangential. We square them both. And I just gotta say it again, notice if you square this and then square root it, the units will work out. So everything gets squared, everything gets, the square root applies to everything too. In future classes, you'll need this. Okay, so now we have the magnitude of the acceleration, right? And now we know we need to find the direction, and we know that that's going to be the tangent, and the tangent will always be, what is it, TOA, opposite over adjacent? Yeah. Okay. So we draw out our circle of where our car is, and you can put the car here or you can put the car there. As long as you resolve its components, it makes sense. So you have your tangential vector, your tangential acceleration. This looks like it's going to act as the, what is that? Adjacent, right? Adjacent, opposite. I only know adjacent after I figure out opposite. Yeah. Okay, so now that we have this triangle that represents that represents what our bump in our car is, we can really calculate it. So that angle phi is the inverse tangent opposite over adjacent, and based on our drawing we can see that the opposite is the radial acceleration and the tangent is the adjacent. And now we see a value that acceleration is negative 13.5 degrees. And we can match that up to our drawing, and we see that negative is going to be clockwise from the x-axis and about 13.5 degrees below that x-axis. And it in fact matches our drawing.
So when we say negative 13.5 degrees, is the acceleration, the total acceleration?
Yeah, that's right. It's this dark purple vector here.
Can you show us like what that being a negative indicates? Like
yeah. Yeah, I can. Hold on. So here, when you're at the top of this hill, you have an acceleration that's pushing you forward, but you also have a center-seeking acceleration that's probably due to gravity here. So your acceleration will be in that direction here. So as it'll show you the motion of the car. And this is really good to understand when you're exiting a freeway on a ramp, right? And your car forcefully is following the direction of this ramp. But notice which way your body moves, and notice which way the things that are hanging on your mirror move. They're gonna move
other way.
Yeah, they're gonna move with some direction that's not being forcefully held to this path. And this would be the direction you would see. Or if your seatbelt's not holding you in, you feel yourself moving a different direction. That's the total acceleration that you're feeling.
And is that why, like on racetracks and on those things, they bank them heavily so that then the gravity is going downward rather than?
Yes, I love that. I do that all the time on the freeway in a very safe way. I let go of the wheel, of the steering wheel, and if you ever notice on a large curve, a large turn, your car will almost naturally go with it, and it's because they curve it, and they curve it so that you follow that motion, and that all has to do with this. If you don't believe me, this vertical hump can very much be translated to a horizontal hump, right? Like if you're, I don't know how to draw that, but yeah, I don't know how to draw that, but this vertical hump is the same exact thing, but if you apply it to the horizontal, that's the way you are curving around a freeway. Okay, good news, everyone. Finito. Chapter 4 is done. Questions I can come back to? Anything? Okay. Would you all like?
Oh, I had a quick I had a quick question.
Yeah.
For the angular speed, you said the units is hertz. So would you want those answers in hertz then?
You should keep them in per second. It's better to keep them in per second, and it's probably what you're going to see in the textbook until you get to maybe the very end of, until we get to waves. If we ever get to waves in this class or in Physics 103, then you'll start using hertz. Yeah, but for now, angular speed, I would write it per second. Yeah,
if we were to write, say, radian per second on a test and box that, are we going to be marked wrong?
No, you won't be marked wrong, because I know it's correct. If here's the only thing I want to just make sure you really get is that once in a while, some of the questions in the book will ask you for an angular speed, and it'll want it in a value or a unit that is like meters per second, and that doesn't sound right to us, but they're giving it to you in that unit, and all that's changing is the unit and the way they're describing it. But the go-to unit for angular speed is per second, 1/second. But whatever the problem tells you, you follow along.
So if we were to, like, how would you, meters per second, how does that work? Like,
it's literally just putting in the meter instead throughout.
Of the radian.
Huh?
Instead of the radian?
Yes, but you're solving, it's still in circular motion. In fact, the problem will probably tell you what is the angular speed in meters per second. And so
is that meter then corresponding to the circumference?
It's still
a part of the.
It's still corresponding to radial motion. So you're still solving everything in terms of radian. You're still moving 2 pi r across the circle, but it just wants it in meters. Yeah. I only say this because I've come across a few problems in the textbook that say that, and it threw me off. You know, like why?
like if you know, like if you're moving around a large circle at a certain meters per second, but then you move, if you do that same meters per second at a smaller circle, you're moving more radians than per second than you were if you were at that bigger circle. Or no, the radians are the same, but the speed would be faster, right?
The radians are the same, but the speed would be faster.
Like 1 degree on a very small circle is really fast, but 1 degree on a very large circle is really slow. You won't cover as much ground as you would on a very small circle.
Yeah, that's right.
But like the angle though being in degrees makes a lot of sense, or being in degrees of radians, but when you said meters, that kind of throws me off a lot.
Yeah, I totally get it, and it's merely a wording issue, and it does not negate anything of what we've just said for circular motion and solving in terms of circles. But sometimes they just give you that unit in meters, and I've seen it even in the test bank questions, solve for angular speed in meters, and it's solved exactly the same way as if it were in radians.
So they put the pies and everything in the same?
Yeah, everything exactly the same. But, you know, they're trying to get you used to the unit of something over second. No matter what it is per second, it's moving. Yeah, it's they're totally messing with you. So I hear you, but I'm telling you that it's happened. Okay, would you like maybe a 5 or 10 minute break, or can we move on to the labs for today? I'll take a
We can do labs.
Okay, I have 1 vote for labs. I hear silence everywhere else. Okay, lab. Keep going. Got it. Okay, so I'll do the Sudoku one last because some of you already know how to play Sudoku, and instead I'll do the second lab that I actually haven't published yet. So let me just publish it. But
so we did have 2 labs, am I to understand now? Like 1 from yesterday and 1 from today?
That's correct. And I'll explain both today. But again, both are, oh my God, why can't I click on it? Both are problem solving type labs. So I think you could finish both today. Let me just download them, and then I'm going to show you. Oh God. I download them from the Canvas because it's faster than than me trying to find them in all my files. Okay, let me go into student mode and I will show you what I have.
You have a Mac, right?
I do.
You can press Command to spacebar and search for anything on your whole computer.
Command spacebar. The
Yeah.
thing is, I also have a naming scheme. I really do. But
Yeah.
when I start naming things all kinds of weird names, for example, the Sudoku one is called the physics challenge. You think I would have called it Sudoku, but I didn't.
As long as you know like something that's in the title, that indexing works pretty well. Because it like also it filters by like most recent, things like that, and like
Huh?
and then it gives you like what type of file or what type of apps, like it breaks it down pretty well.
Yeah, I will use it. Command spacebar. Thank you.
No problem.
Okay, so what you see now is my thing, and yes, I know I have a lot of tabs, and leave me alone. So this is our page right now, and so you have everything available to you to start the labs and the homework. The lab for chapter 5 I'll show you tomorrow. Okay, so let me start with the second one. So in this problem, this lab that we're going to do, we're not going to solve any problems completely the full way through with numbers. We just want to isolate variables and identify variables. So this is a problem solving type lab. Many of the problems, I don't know if this is big enough. Okay, there. Many of the problems that we want to solve involve several variables that we must identify. We saw that today. We will develop a method to solve complicated problems by first identifying all the variables. Use the example to help you complete the assignment. And then your assignment may be typed or written and converted to a PDF, of course. So let me show you the example. And ay Dios mío, there's so many. Zoom is like, I think Zoom is giving me vertigo because this is, Jesus. Okay, so we have an example problem. Do we? Yes, we do. Okay, so here's an example problem that you'll see in your work. When an F-14 airplane takes off from an aircraft carrier, it is literally catapulted off the flight deck. The plane's final speed at takeoff is 68.2 meters per second. The F-14 airplane starts from rest. The plane accelerates in 2 seconds and has a mass of 29,545 kilograms. What is the total force that gets the F-14 in the air? First, I'll say that I recognize you do not know force and you do not know the equations of force, but I'm just going to give them to you. We don't need to know those concepts to complete this assignment. I'll show you. Okay, so the first thing I want you to do whenever you see a problem is to really read the word problem and identify what are all the variables. And you can do this in several ways by underlining, highlighting, or the preferred method is to make a nice list, right? So make a list of what are the given variables, and you see the final velocity is 68.2 meters per second. The initial velocity is told to us from rest, so that's 0. The time is 2 seconds, and the mass is given to us also. Notice this list is written with proper notation, with the numbers given to us exactly, and with the units. Now you want to figure out what it is that you're solving for. I always highlight this in green. So we're solving for force, right? And so in the next chapter, we're going to learn that the equation is F equals ma. So you're solving for this, and the equations that are available to you in this situation is just F equals ma. So what you need to solve for here is that acceleration, because you don't have that. So we need to find A, and you solve for A using your kinematic equation, right? So now you have 2 equations. The next thing you would do for any problem is completely solve it out so that all you have to do is plug everything in. So we solve for acceleration here, we isolate acceleration, and there's our equation. And now we solve for the force, which was the original thing. So F equals ma, we put in the equation for A, and this is your solution. And this will be in the solution, the unit of Newton. The unit of Newton is kilogram meter per second squared. Notice that it's in brackets. And so this is then the solution for the first problem or a problem in the lab. You would want to show how to solve for the problem, but not actually solve it. And you want to show that by listing the given variables, what it is you're solving for, what are the equations needed, and then solve for that exact answer using all the equations. This is the last step I really want to see, and I really want you to get to, is here. Because especially in later classes, you're going to get so many variables and so many equations that you don't want to work with numbers. You want to work with the equation until it's time to plug everything in. And at this point, you have the mass, you have the final velocity, you have the initial velocity, you have the time. You're ready to use the calculator, right? So that's the entire lab, and you have about 5 problems of that to solve for, and use that step-by-step process. So let me show you the assignment super quickly, and you'll see hopefully that I've emphasized that in the problem too.
And and this is, you said we'll have like 2 labs a week. This is our second one, and so we won't have another one tomorrow, right?
No, you have 2 labs a week, and this is half of the lab for chapter 4. The second half is the Sudoku. So
okay. So it's 1 lab.
Notice this is part 2 of lab 1, and 1 is the Sudoku. Okay, so here is the directions again. For each problem, identify and list the given values, the variables you're going to solve for in the equations. Then isolate for the variables that you need and actually solve the problem. Do not solve the problem for a numerical value. Just write what it's equal to. Yeah, and you'll see 1, 2, 3, 4, 5 problems. All of these problems are either from your textbook or are common physics problems. So I'll just outright, the solutions are out there. Use them as a guide, but only as a guide. Attempt them by yourself, and see how that works. Okay, any questions about this? I actually don't see my chat window, sorry. Okay, I see the chat window. Okay, so that is the first part. I'm sorry, that's the second part. The last, I'm getting all messed up here. Part 1 is the Sudoku puzzle. And if you know how to play Sudoku and you feel very confident with solving the Sudoku problems, class is over and you're free to go. I'm going to keep recording and I'm going to explain Sudoku for anyone who hasn't played it. But let me just show you the assignment first, and then I'll give you directions to Sudoku however it is needed. I see a question. Sanjita, question, yes.
It's like a separate question. So when turning in lab, the Sudoku lab, I accidentally first submitted it into the homework problem set 1.
Yeah, so Sanjita, this is a question specific to you, and I actually tried to respond in the chat, but it didn't go.
I was accidentally kicked out first. That's why I think I didn't see it.
It's totally fine. So for your situation, just email me that kind of stuff, or I can help you at the end.
Okay.
Okay.
Thank you.
Actually, dang, I deleted the response, but I had it in there. Okay, yes, if you're good with knowing how to do Sudoku and playing it, you're free to go. Please, yeah, go ahead. Okay, so this is the assignment. You want to solve the Sudoku puzzle, and there are 3 puzzles on here: beginner, intermediate, advanced. You want to solve 2 of them, any 2 of them, and take your time with it. Don't find a solution for it. You could ask people for help, but don't get the actual answer. And the goal of this is 100% just a cognitive process and working through seemingly impossible problems, knowing that there is a solution. And sometimes you have to take a break and get a whole new view of it. Okay, so that's the actual assignment, and there are directions that go with that. The directions are in this PowerPoint here, which I'm going to show you in just a second. I think I'm going to show you. Oy, 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 oy. Where is all my stuff? Thought I downloaded it. Okay, it's opening. Maybe I need water or something. Okay, so the point of Sudoku and solving Sudoku, and I'm happy to hear any comments about this. And then I can work with you guys individually if you have any specific questions to you. Okay, so I hope you see the screen now. And again, Sudoku is just a challenge that it's going to help you, get used to numbers, analyzing spatial relationships, which means keeping things spatially in a certain position. Patterns and sequencing, it's Sudoku, right? It helps our brain kind of keep going. So Sudoku is a number place game that became popular in Japan and then moved over from the UK to the US. And there's so many other versions. Anyone out there play Kakuro? That's the one I play. But yeah, Sudoku is the straightforward one. And question, are you going to grade Sudoku Lab on completion or on correctness? I'll probably grade it on both. I scan the Sudoku really quickly, but it will be graded on completion, of course. But I will scan it quickly to see if it's correct, especially when it's a simple assignment, I think, or something that is, you devote time and it'll get done. Okay, so how do we complete Sudoku? Here's an example. Your goal is to fill in the grid so that every single row, column, and box each contain the numbers 1 through 9. Here is a row, and that row needs to contain the numbers 1 through 9. Here is a column, and that column needs to contain the numbers 1 through 9. And then here is a box, a 3x3 box, and that needs to also contain the numbers 1 through 9. And it cannot repeat between row, box, and column. Okay, so for our first example, anyone want to guess what number should go here? Any guesses? Any guesses? I don't remember. Okay, well let's look at the line, right? The line has the numbers 1 through 9, and what's missing is number 1, 2, and 3. It looks like. Is that right? That's the row.
So it has to be 1.
Yeah, I think it's 1, right? Because the row is 1, 2, 3 is missing, and if you look at the column already has 2 and 3. So yeah, it has to be 1. So we could fill that in with the 1, right? And that's the directions. The row is missing 1, 2, 3, and 2 and 3 already appear in the column. Yeah, so the answer is 1. And then you can keep doing the same thing for each one. That one should be number 3. It should be number 3 because the only options are 2 and 3, and in this cube, 2 is already there, so it must be 3. And so then that leaves us with number 2 next to it, right? And so you continue, you can kind of move so on. And so there's a solution for this one if you want to practice it.
There's only one correct solution?
Yes, yes.
Oh my God, that's why I always end up having to change everything multiple times and then I give up.
Yeah, so this is just like physics in that there are multiple ways to get the answer, but there's only one answer that physically describes what's happening. Yeah. And so your goal is just to complete 2 out of the 3 Sudokus. Yeah. That's it.
Which 2 are the easiest ones?
What?
Which 2 are the easiest ones?
The top.
Like, the less advanced, the top 2?
Yes, beginner and intermediate. Okay, guys, I'm going to officially stop recording and then I'll stick around for anyone that has any specific questions. And I'm happy to help with anything at all. Yes, use a pencil for sure. Yeah. Have fun with the Sudoku. Step away if you need to. Yeah.
Thank you, I will. I'm going to go do Sudoku right now.
Yeah, enjoy, Keon. Enjoy it. Bye, guys. Bye, Gary and Isla and Robin. Have a good day, guys. Thank you, Alex. Yeah. the Sudoku is a really good way to test your patience too. You know, walk away, come back. Walk
I know. Mine failed.
away.
I know I have terrible patience. My impulse control is off the. It's off the charts. It's so low.
But I'm really surprised. Let me just stop. Did I already stop recording? Where's my button? My chat window all of a sudden became huge, and now I can't see anything. Oh, there it is. There it is. Okay, stop recording. I just want the obvious button.